Welcome everybody to Lab 12. This week we're going to be going over how to create scatter plots in PSPP, as well as how to run bivariate correlations between two continuous variables. For today's example, we're going to be using the same problem that we saw in class, the correlation example regarding strangers' self-disclosure and liking for the stranger. That is a study where a professor takes 10 individuals, has them talk to a new person. This new stranger self-discloses a certain amount, and then the participants themselves rate how much they like that stranger. What we're trying to figure out is whether increases in self-disclosure result in any kind of change or are related to any kind of change in the liking of strangers. Does greater self-disclosure lead to greater liking? Does less self-disclosure lead to more liking? We're trying to see if there is a relationship between the two. So we're going to be using that example in our Lab 12 data set. So if you go ahead and open up that, you will see that this data set has three variables. The first is the subject or participant number. The second is the scores on self-disclosure that the researchers rated, 1 through 10. And the third is the liking variable, where the participants indicated how much they liked the stranger. And we can go to our data view, and we can see here that we have the 10 subjects, as well as all of those scores for self-disclosure and the scores for liking. Now, in the past, we have simply run descriptives or run some kind of analysis of different means between the two groups. And we could do the same thing here. These are continuous variables, and so they do in fact have a meaningful average. There is an average amount of self-disclosure across the 10 strangers and an average amount of liking that the participants experience towards those strangers. And so we could go about looking at these descriptives the same way we have in the past, where we go to Analyze, Descriptive Statistics, Descriptives, and then we'll move over the self-disclosure variable and the liking variable. And let's go ahead and set it to just have the mean and standard deviation. Click OK. And here we see in our output the syntax we're used to seeing, as well as the descriptives with the n, the mean, and the standard deviation. So the sample size, the mean, and the standard deviation. And this indicates that the average amount of self-disclosure on a 1 to 10 scale was a little bit above the midpoint at 5.8. And the average amount of liking of these strangers was, a bit more above the midpoint on this 1 to 10 scale of about a 6.6. So in general, people seem to be favorable towards the strangers, and the strangers seem to disclose a little bit more than they didn't disclose. But again, what we're trying to ask here isn't about whether there was more disclosure or more liking. These are two different variables that wouldn't make sense to see if there was a mean difference. We're not comparing these two things. What we want to find is, does change in one associate with change in the other? And so the first thing we're going to do is look at how they're related visually by doing a scatter plot. So if we go to our Lab 12 data again, this time we're going to go to Graphs. And we're going to choose the obvious choice, which is scatter plot. This is going to open a new window. And in this window, you are simply going to tell it what variable do you want on your y-axis as your y variable, and what do you want on the x-axis as your x variable. Reminder that the y-axis is going to be the vertical axis, so on the left side of the graph, whereas your x-axis is going to be that horizontal axis along the bottom of your graph. So if we are choosing self-disclosure as our x variable, we're going to move it along here to be on the bottom, and liking we move to be our y-axis. We don't have any other options of what to choose, so we'll just click OK. And we will go to our PSPP output, and here is the graph. Now it's not that visually appealing. You can see how some of the dots are up along the top, and this last dot is right along the edge of that 10 point. But it does match on to what we were able to graph in class, what we see here from class. So we can go back to the PSPP, and even though it's not as visually appealing, we can still see we're looking for the form, which this doesn't look like a curvilinear. This looks like it might have some upward trend, some linear trend. We also, again, see the upward, so this is probably going to be some kind of positive relationship. And if we drew a best fit line kind of running through, it seems like it's kind of off from the points, but there is clearly a movement in the upward direction. So what we're going to calculate is the strength. How much do these points deviate from an imaginary hypothetical best fit line that goes through the data? To do that, we need to run a bivariate correlation. So we'll go back to our data set, and here we're going to analyze a bivariate correlation. So we're trying to find out something about our data. We'll go to Analyze, Bivariate Correlation. It's not even its own grouping, it's just straight out as a bivariate correlation. And when we click this, it'll open up a new window. And here we have the variable box that has all of our current variables, as well as an open box. It doesn't have any labels on it, any titles. That's because you're just going to put in any variables that you want associated with each other. And all of the variables you're going to put in are going to create some pairwise comparisons. So for right now, we're just going to put in 2 different variables. But if we were to put in 3 or more, it would create every combination possible. So in this case, it's going to link self-disclosure to liking. But we would also, if we had a third variable, it would link self-disclosure to that third variable and liking to that third variable. So you can insert as many as you want. We also need to look down here at the tests of significance, whether it's two-tailed or one-tailed. So whether we're expecting a direction. A two-tailed would imply that we are curious if there is a relationship, but we don't know whether it will be positive or negative. It's on either end of the +1, -1 spectrum. But if we have a specific hypothesis, we think that it's going to be either negative or positive. So maybe we think that increases in self-disclosure are positively related to liking. Then we would have a specific hypothesis, and we would click the one-tailed version. In this situation, we're just going to run a two-tailed because we didn't have a specific hypothesis. We also have this nice tool here where we can tell PSPP to flag the significant correlations. This just means that any correlations that are significant at 0.05, which is our standard alpha, it's going to put a little asterisk, a little marker there that says, hey, pay attention here. So we have all the information we need. Again, you could include more variables, but for now, we just have the 2 that we're going to look at. So we click OK. And this is going to pull up a correlation table. So here we have our syntax with the keyword correlation. It's going to put in the variables are going to equal any of the many variables we're looking at. And again, there's going to be a pairwise between every combination. And we're asking it to print both a two-tailed test as well as this non-significance, the noting the significance. And here you'll see, here's this asterisk. Those are representing significant at 0.05 level. Sorry, not an asterisk, a little letter A. A for significant at 0.05. All right, so I just said that this was significant, but how do we know? The way a correlation table in PSPP works is that each cell is going to refer to the row of one variable and the column of another. So in this case, we have how is stranger's self-disclosure related to stranger's self-disclosure. And we know that anything related to itself, if you have increases in stranger's self-disclosure, well, those are going to be the same increases on that variable. It's related to itself. So it's going to be a perfect positive 1.0. Okay, so this is more of a conceptual issue that anything related to itself is a perfect positive 1 correlation. So here we see in this top row of the cell, we see the actual Pearson correlation. This is your R value. You also might find a significance value, the two-tailed, but in this case it's not going to do a significance because it's the same variable, and we have how many participants it took to figure out that it was perfectly related. So when you are looking at a correlation table, there will always be a diagonal going across your table that in that diagonal are always going to be Pearson correlations of 1. For instance, in this lower corner, you will see liking for stranger correlated to liking for stranger. But what we are really interested in is the stuff off of the diagonal. So here in this cell, this top right cell, we will see how stranger's self-disclosure, as our X variable, is related to liking for stranger. And here is our answer. this R value is going to be a 0.69. And as you will remember, an R value of 0.69 is what we will consider a strong relationship. We also will see the significance of 0.026. The significance two-tailed, as we'll remember from t-tests and from ANOVAs, is the same as saying a p-value. So here we have a p-value, a probability of getting this result, of getting a 0.69 R value, assuming that we should have gotten a 0 in the real world. The probability of getting this 0.69 is a 0.026, which is less than 0.05, hence that little a superscript there for significant at 0.05 level. And finally, the n of 10, that's how many people you have, which you would subtract 2 to get the degrees of freedom. Because it's always degrees of freedom in a correlation is the total n, or the total number of participants minus 2. So this is with stranger self-disclosure as the x and liking for stranger as the y. But if we go to the bottom of the correlation table, the bottom left, we will see those exact same numbers, the 0.69 Pearson correlation, the 0.026 p-value, the n of 10, and the superscript of significant at 0.05. And that's because in here we have liking for stranger as the x and stranger's self-disclosure as the y. Because we know in a bivariate correlation, it does not matter whether it's the x or the y, which variable is the x and which variable is the y. At the end of the day, they are going to get you the same result. That's actually all you need to know for running correlations. First, always create a scatter plot where you can visualize whether or not you're expecting a curvilinear or a linear relationship and whether you're expecting it to be positive or negative. And then using that analyze bivariate correlation to put in your variables and knowing how to read these tables. You would then report it by indicating all of these elements. So reporting your R statistic and your p-value, also indicating whether it is positive or negative and whether it is a strong or a weak variable. So here we would say we were going to reject the null hypothesis, and we find that as stranger self-disclosure increases, so does the liking of the stranger, with an R of 8 degrees of freedom equals a 0.69, and the p-value equals 0.026. So on the exercise this week, you have to input your own data, and, well, the data I've given you, and you have to run correlations between multiple variables, multiple bivariate correlations, and generate that output. Best of luck.